So today we're going to talk about constraint satisfaction problems. This is going to be a different way of representing problems. So up until now we've been thinking about problems in terms of state space search. So if we had a particular problem, we would formalize it in terms of a set of discrete states and actions that moved us between states. And in a sense, those states were atomic, right? We were not able to sort of look inside of a state and look at the different factors that influenced what state we were in. We just had these atomic states and we moved between them. And the nice thing about that formalism is that it's very flexible, right? Almost any problem that you can think of can be expressed in terms of states and transitions between states. It's not always the best approach, though. So when I've got this giant atomic state, one issue is that I can end up with lots of them, right? I can have this state space explosion when my state is depending on a lot of underlying variables, and we've seen some examples of that. So in general, every time I add one bit of information, it doubles the number of states that I have to deal with. Another issue is that there might be structure inside those states that would be useful in finding solutions, and if I'm not considering that structure, I might be working harder than I need to. So to be concrete, imagine for a second that the problem that I'm faced with is organizing a group of students or a classroom of students into groups. So I might have some requirements about the groups that I want to set up. I might want to make sure that all the first years are together in their own groups, and I might want to make sure that students who are in the same group don't have conflicting schedules so they can all get together and meet. So we could formulate a problem like that in terms of state space search, right? A state then would be an assignment of all students to groups, and then an action might say switch students from one group to another, so exchange students between two groups. So the size of that state space would be the number of possible assignments of students to groups. And the size of the action space would be pretty big, right? It would be all of the possible exchanges that I might make. And it's possible to solve the problem that way, but it's not the best way to solve the problem. It's not the way you and I would think about solving the problem, right? Because we can't take advantage of the structure. We can't look at the problem and say, well, you know, I recognize that all of the first years have to be together in groups, so let me separate them all out first, put those students in groups, and let's reduce the size of the problem that I have to deal with in the remainder of the class. I could also do things like, let's pick out the student with the most constrained schedule and make sure that he's in a group that works for him before I move on to the next, to the rest of the students. And if I'm just viewing this as a monolithic state space, I don't have the flexibility to break the problem down like that. So that's the sort of intuition behind why constraint satisfaction might be a nice way to look at problems versus the kind of graph search that we've been looking at before. So let's just skim through the chapter here to get some of the terminology down. We're looking at chapter 4, features and states. So this is sort of making the point that I just made. So we're going to be thinking in terms of assigning correct values to variables, and the variables are going to be features. So we've got some features of a problem, and all of those features together would constitute what we would have thought of as the state before. Those variables or features will have a domain, so they'll have different values that those variables might take on. And this is making the point that I was making a second ago, that if you have binary features that have the domain of binary values, then a fairly small number of features can lead to what would be a pretty giant number of states. So there's an advantage, right? This alone is an advantage to thinking in terms of features rather than thinking in terms of states. So a possible world is going to be a possible solution to the problem that we're dealing with. It's going to be a single assignment to all of the variables that represent the problem. Right? The domain is going to be, for a particular variable, will be all of the possible values that that variable could take on. We'll mostly today be thinking in terms of discrete variables. We could address constraint satisfaction problems with continuous variables, but we won't for now. Good. And so we need a way of expressing constraints, the constraints on our variables. So in general, we'll have some set of constraints. A set of constraints will have a scope, so not every constraint will apply to every variable. So the scope of a constraint is the set of variables it applies to. And a tuple is how we're going to express a particular constraint. It's a set of assignments that corresponds to that constraint. So the best thing to do, I think, is to look at an example. So here's a constraint with the scope A, B, C. So this is a constraint that applies to 3 variables, A and B and C. And if this is actually listing all the possible valid assignments to those 3 variables. So this is a constraint on the values that those 3 variables can take on. A can be 1 or 2, but if A is 2, B has to be 2 and C has to be 4. So here we're extensionally expressing a constraint. We're actually listing all of the possible values that could satisfy that constraint in a table. More commonly, we would intentionally express a constraint, right? This becomes quite cumbersome, so we can express a constraint sort of logically by describing that constraint, right? So this turns out to be this same constraint, but described using logical notation. So we can talk about unary constraints that apply to only one variable, binary constraints that relate 2 variables to each other, and we could have n-ary constraints that relate lots of variables to each other. We can talk about a possible world, right? An assignment of variables satisfying a set of constraints. That's going to be sort of a solution. That world would be a model of the constraints, just to get that terminology down. Okay. So that brings us to what the actual definition of a constraint satisfaction problem. A constraint satisfaction problem is exactly a set of variables, a domain for each variable, and a set of constraints. So that's the input to the problem, and there are different kinds of output we might want. Typically we'll want to find a model, right? We'll want to find a solution that satisfies all the constraints, or we'll want to find all of the models, all of the assignments to the variables that satisfy all of the constraints. So we're going pretty fast here, and one of the things that we are not going to do in this course is program constraint satisfaction problem solvers. There are a couple of reasons for that. One reason is, we only have so much time. We've got to choose our battles. Another reason is that it's a fairly big task. So as you'll see as you skim through this chapter, there are several different algorithms that can be brought to bear on this problem. And each of those algorithms have some variations that can make them more or less efficient. And if we really want to write a very powerful constraint satisfaction problem solver, it's probably going to require us to bring together several different approaches, so some combination of the algorithms that we're going to see. So when we were thinking about A star, we could sit down and in 20 or 30 lines of code, we could write the A star algorithm. And it's optimal in some sense. Our A star algorithm is as good as anybody's A star algorithm. When we're thinking about constraint satisfaction problems, right, what we will typically do if we had such a problem that we wanted to solve is not sit down and try to write the best solver we can. We would go out and find an off-the-shelf constraint satisfaction problem solver that's been, highly tuned and optimized over years of work. So we're more interested in thinking about how to express problems as constraint satisfaction problems, and we want to have sort of a general idea of the kinds of mechanisms that these solvers would use. But this isn't a case where it really makes sense to sit down and write our own solver, and we won't in this course. So with that in mind, let's take a quick look at the kinds of techniques that we might use to build such a solver, and the kinds of techniques that existing solvers actually use. So one approach might be generate and test. This is sort of a straw man approach. This is not something that you would actually try for an efficient solver. And this is basically just saying, we can solve constraint satisfaction problems by systematically trying every variable assignment and checking them all against the set of constraints that we have. So that's obviously not going to be a very efficient approach, right? So this is pointing out that if we have four variables and they each have 5 possible assignments, then we're already up to 1,000 different variable assignments to test. And we basically just have to try them all. This might be okay if there are lots and lots of assignments that satisfy our constraints. if we're looking for a needle in a haystack, it's going to take an exponentially large amount of time in general to use this approach, so it's no good. So we can use search. We can use depth-first search to find assignments that work. And this is going to be a slightly better approach. So I think there's no better way to deal with this than to just look at this example. So here, the constraint satisfaction problem that we're trying to solve is from example 413. Let's take a look at it. Oh, it's expressed here. So we have 3 variables, A, B, and C, with the domain 1, 2, 3, 4 for each variable. And we have only 2 constraints, that A has to be less than B and B has to be less than C. So one approach to solving this is to just try picking assignments to each variable one at a time, and then doing a depth-first search where each layer of the search represents moving on to the next assignment, to the next variable. So let's just step through what might happen here. Let's say for whatever reason we're starting our search with an assignment for B, so we pick the first possible assignment to B, which is 1. And then we move on to the first assignment for A. And we recognize at this point that we violated one of our constraints, right? One of our constraints is that A be less than B. This violates that constraint, so it doesn't work. So we backtrack, right? We stop searching at this point. And notice this is why this search approach is more efficient than the generate a test and test approach we saw a second ago. We can recognize before we've tried all of these possibilities that we're heading down a path that isn't productive. So we can avoid checking lots of possibilities sort of below this point in the tree, which wasn't something that we were able to do with generate and test. So none of these are going to work out, so we'd backtrack up here. We would then try the second assignment for B2. Again, we'll try A1. No violation there. A1 is less than B2. Next, we'll try to assign 1 to C1. Well, that doesn't work because that violates this constraint. Right? B has to be less than C, but it isn't in this case. It isn't in this case. It is here. And here we've found an assignment of all 3 variables that actually satisfies our 2 constraints, so that's checked here. So if we just wanted to find one assignment, we could stop at this point and we would have found an assignment pretty quickly. This figure is assuming that we want to find all of the valid assignments. So it's going to continue with this depth-first traversal of this search tree, and it will find 4 assignments total that work. So that's pretty good. That's an improvement. We can do a little bit better, or at least we can try something else. We can apply one of these consistency algorithms. So the idea here is that we're going to create a graph that's going to represent all of our variables as well as the set of constraints. So both variables and constraints are going to show up in this graph. And that graph is going to help us visualize the process of finding satisfying solutions. So in this case, we're not really looking for a satisfying assignment. What we're doing is we're going to progressively reduce the domain of our variables. We're going to find out if there's some possible assignment to a variable that can't hold. We'll remove that from the domain, and then we'll continue that process. So the advantage of that over the search algorithm that we saw before, the potential advantage of that, is that if we can recognize that a particular variable assignment is not going to work out under any circumstances, we can exclude it forever from our search process, right? So if we think back to that search algorithm we saw before, B2 is never, A4 is never a possibility, because if A is equal to 4, then it can never be less than B. But we have to rediscover that here, and then here, and then here, right? So if we'd been able to figure out beforehand that A4 wasn't going to work out, we wouldn't have to keep retrying that dead-end alternative. And that's the idea behind this consistency checking approach. So the book outlines an algorithm for doing this. That algorithm is here. I'll let you take a minute to read it over and to read over the description of the algorithm. And it also has a nice little example where it steps through that algorithm for that same problem that we executed, or that we looked at when we were looking at graph search. So I think what I'll do is I'll try to sort of step through that algorithm as well. So let me bring up the constraint graph, the constraint network that corresponds to that problem. So how do we construct this graph? There's going to be a node for every variable, a node for every constraint, and those arcs, and an arc from every variable to any constraint that involves that variable. So for some reason he doesn't like to draw these things as directed arcs, but why not? Let's put the directions in here. So this would look like this. So now every variable has an arc from that variable to all of the constraints that involve that variable. So B is involved in 2 constraints, so it has arcs leading to these 2 constraints. So how does the algorithm work? Well, the first thing that we need to do is be keeping track of the current domain of all of the variables. So we have these 3 variables, A, B, and C. And initially, the domain for all 3 is 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And what's going to happen is that as we work our way through the algorithm, the domain of these things is going to be shrunken down until, hopefully, for some problems, we'll be able to get to the point where there's only 1 element in the domain of each variable, in which case we found a solution. And even if we don't get to that point, well, we've made some progress. So the first step in the algorithm is to stick all of these arcs into a set that we can then pull them out of one at a time. And then we proceed through the algorithm by repeatedly removing arcs from the set and then examining that variable and that constraint to see if it's possible to reduce the domain of that variable. So let's start by removing this constraint, or this arc. So this is the arc from A to A is less than B, and we want to look here to see if there are any assignments to A that don't make sense given that constraint. And in this case, there is one. It's not possible for A to take on the value 4, because if A were 4, there's no way for there to be any of these values for B that would make A less than B, right? So this just doesn't work. So progress, right? Now we know that A has to be 1 or 2 or 3. It can't be 4. Okay, so now there are only 3 arcs left. So we'll move on and we'll remove another one. So let's choose this one. And at this point, we're looking to see if there's any possibility that we can reduce the domain of B by looking at this constraint A is less than B. And there is, right? So here, B can't take on the value 1, because if it did, there'd be no way for A to get under that, right? So it can't be B, or it can't be 1. So great, progress. Now, at this point, we have to be a little bit careful, right? Because we changed the domain of B, that might make it possible to go back and look at some other arc and further reduce the domain of some other variable. So in general, what we do at this point is we put any arcs back in that depend on the same variables that involved in that constraint. In this case, that would be A, right? So A goes back into play. Now, unfortunately, when we look at A, this didn't actually exclude any more values of A, right? Because 1, 2, or 3, any of those can get under some value in B. So when A comes back off and we consider that arc again, we're not actually able to remove any additional elements from the domain of A. So, but now we're making progress. We've only got 2 of these arcs left to be removed. So let's just sort of work from left to right here, and we'll remove this one. And now we want to check to see if we can remove any values from the domain of B based on this constraint, B is less than C. And again, so it looks like 4 is going to be able to go, right? Because if there's no way for B to take on the value of 4 and still be less than C. So that's good. But now we've changed the domain of B again, so this guy, right, this constraint that involves A has to go back in. Sorry, let's keep that blue. And I guess this guy probably has to go back in too, because that constraint involves B as well. So we'll grab this guy. It's a little bit tedious, but you see where we're going, hopefully, right? This is getting smaller and smaller every time. And it turns out that, I've been sort of arbitrarily picking the order that I'm pulling these arcs off. And it turns out that it doesn't matter what order you choose. You're going to get to the same minimal set regardless. So in this case, I'm looking at A, and the constraint A is less than B. So A now cannot be 3, because then it wouldn't be possible for A to be less than B, right? No matter what value I picked for B, that wouldn't hold. So that's good, that's progress. I get to remove another value from A. Very good, and I guess that means that this guy goes back in. I might be making some mistakes here, but hopefully we're on the right track. So now let's pull this guy out. A is less than B. Did anything change here? No, it wouldn't, right? Because those two are related in such a way that it can. Let's now pull this guy out. Now, is it possible to remove anything from the domain of B? No, because nothing's changed over here at C. So the only one's that's left here is C. So we'll remove that one. Can I remove anything from the domain of C, given that B has to be less than C? Well, let's get back to my ink here. So C probably can't be 1, because then B could not be less than that, right? C also can't be 2, because it couldn't be less than that. Could be 3 or 4. And it turns out that this is going to be the final state after we run this whole thing. So we haven't quite gotten we haven't gotten the domain of A or B or C down to 1 element. So in this case, this consistency algorithm isn't enough to actually solve the problem. Sometimes it will be, but in this case it isn't. But now we have the option of running our search algorithm from this point, and the search problem is going to be simplified because we've thrown out a lot of these possibilities.